So I'm going to go ahead and just read the names of the panelists, and then as we go through, let them introduce themselves. First, I'm just going to start with the list as I have it. I don't have any idea how it actually wound up in this order, but that's fine. So we'll start with Tom Nugent from PowerLight Technologies. So Tom, you're ready to go. You can introduce yourself for a couple minutes, and I think you have something to share. Perfect.
Yes. Thank you to the entire LSIC team for this event. Thanks to Wes and Andrea for sort of squeezing me in at the last minute. And also thanks Jeff Landis for a great introduction to laser power beaming yesterday. I'm Tom Nugent from PowerLight Technologies, CTO and co-founder. We were formerly known as Laser Motive, and we won the NASA Centennial Challenge for Power Beaming back in 2009. I'll have pictures of that in a little bit. We changed our name a few years ago as part of our shift towards commercializing this technology. So briefly, we've been doing hardware demonstrations for the last 12 years, some of which, but not all of which, are shown here. We have flown drones. We've sent laser power over fiber to underwater vehicles. We've powered remote sensors and others. And we've had validation through a number of partners, and sometimes a sponsorship through a variety of partners, some of whom are shown down below. And there's a number of presentations that I've done and others that we just haven't had the time to put together into presentations that if people are interested, we can talk more about a variety of these systems we've built. But just to briefly talk about some of the traction, we just recently successfully completed the DoD Patrol program that Paul Jaffe was talking about yesterday. We were the technology provider for that. That program allowed us to do improvements on many metrics that I'll talk about in a moment. And we're working on the follow-on transition to take that technology into productization for the DoD. We're currently engaged with a major telecom customer for 5G infrastructure. And as part of all of this, we've been developing the supply chain for laser power beaming across all of the components and services needed to build quantity scale of this type of hardware. And perhaps of more interest to some of the crowd here, we're currently executing on an SBIR for NASA on power beaming for lunar operations. One of our areas of particular expertise is on the power receivers, some of which are shown here. And we have been able to demonstrate high array level efficiency, which is the efficiency that's not just the PV cell, but everything else that can affect those performance. High power to weight ratios in order to fly on UAVs. We've had systems that are weather resistant and safe as well. And that leads to the other area of our particular expertise is safety. This is not going to be commercialized unless it can be as safe as an extension cord. And really what we are building is a wireless extension cord. And so we have a variety of passive and active features. And we talk about this D3 cycle of the time it takes to detect a potential for an object, decide if it's something that we need to shut off the laser for, and then deactivate the laser. And that system has been tested and verified by third parties, including the Navy's Laser Safety Review Board. Anyone who's actually familiar with laser safety officers will know how paranoid they are. I remember one group talked about something with trying to protect yourself from lava with a tin hat is how they were viewing high power lasers. And we've been able to prove to those folks that we can operate these very high power multi-kilowatt lasers safely around untrained observers without any form of eye protection or other protection. And so that is the other area of our particular expertise. But of course, we build end-to-end systems, and we do the systems engineering approach to optimize that hardware for overall performance across whichever metrics are most important. In some cases, that might be power or distance. In other cases, it might be efficiency or weight or even cost. On the right-hand side here are some of the metrics that we have demonstrated in a variety of hardware that we have built and again, had validated by third parties. Power output at the receiver, up to 1 kilowatt so far. We're looking to scale that into the multiple kilowatt scale in the near future. Distances up to 1 kilometer through free space that we're going to be extending into multiple kilometers again in the next year or so. Power over fiber has been demonstrated up to 100 meters and can scale out to multiple kilometers as well. High power to weight ratios, high power per area. ratios, which again gets to the thermal limits that people have talked about and how to manage the heat on both ends. Again, safety system can react in a millisecond to shut off before anything can approach the beam. There's a lot of metrics around efficiency, one of which that we talk about are all the design factors in the receiver outside of the PV cells, and we have world-leading performance there. We've handed some systems over to partners to install and operate themselves, and they've talked about the user experience actually being great and easy to work with. We have been doing a lot of work with regulatory bodies. The Laser Clearinghouse tries to make sure that you don't shine lasers on satellites. The FDA regulates laser products, and we're in the process with that. And as I mentioned, we've had systems that are resistant to rain and other conditions. And I just want to reiterate, we are building hardware, we're doing field testing. We're not just talking about stuff in theory or ideal lab conditions or talking about just one cherry-picked result. I made this type of chart, gosh, probably starting a decade ago, looking at potential use cases for power beaming. And in some varieties of this, also compare it to microwave and induction and stuff. But if you're looking at systems that have been demonstrated for more than, call it 100 meters or 100 watts, there are very few demonstrations that have been done. And I'd like to thank Paul Jaffe for doing a great job, not only in sort of gathering the data that different groups have published, but also really advocating for the industry to standardize on how they report the results. All the other ones in this scale are microwave power beaming. And the biggest one, of course, was done more than 40 years ago. And all of the laser ones have been done actually by Power Light, and a number of them have been safe and have been advancing not only on these power and distance metrics, but also on things like weight and size. And so these are all notional about some of the different applications, whether it's telecom, remote sensors, aerial vehicles, or others. And from everything that we've heard, including as recently as yesterday in this conference, the scenarios that NASA is looking at for the moon fall sort of within this range of 1 to tens of kilometers, and power levels maybe as low as a few hundred watts for some rovers, but up to tens of kilowatts for some of that ISRU. And this is a regime that we've already started demonstrating in and are pushing further into. And so we think that there is a good possibility of being able to have proven hardware, be able to advance for through all of the timeline necessary to prove it out, excuse me, for operating on the moon. So this panel is about challenges. Just a sort of brief couple of thoughts. Obviously, components always need to improve. Efficiency is one, and there's been a lot of good work that some people have already talked about here. Rating them for space, I know others have talked about that challenge. Thermal management is going to be, I think, a challenge, because when you're talking multi-kilowatt lasers right now, all the industrial ones are using water loops, and so adapting that for space is something that needs to be dealt with. Testing is something that's going to need to be dealt with. There are a number of long distance ranges, but sometimes they're hard to access. So broadening that and then working through the facilities to test in a vacuum and eventually in orbit need to be addressed. Finance, we've been very lucky to have a lot of support from the DoD, but because we all love Congress, we know that the budget sort of tends to fluctuate. And so sometimes funding stops temporarily, and that can really throw a monkey wrench in things. The TRL scale is a very useful one, but I think it's insufficient for communicating and discussing risk of technology development, especially in cases where in some situations, there may be a technology that's sort of well proven. I may talk about rockets as a general class, and you maybe do something new or different with those, but there's a whole industrial base out there. And so the risk may be different from a technology that is still much newer, like laser power beaming, where advancing through the TRL scale is going to have a different rhythm to it. So discussing risk is another challenge, I think, too, to understand on all sides of the equation here. Also, we've had some issues that there's what I think is premature insistence on separable subsystems. Some people say, oh, one group can make the transmitter, one group can make the receiver, and eventually we'll get there. But right now, there's a lot of tight integration between those to optimize performance. And I don't think separating those out is a good way to go early on where we are right now. It's been helpful in this conference for us to understand more about the use cases and these conditions about whether or not you're in permanent shadows, whether or not your receivers are mobile. And then again, I don't know if the Laser Clearinghouse has thought about lasers coming from the moon. Right now, they're all just focused on ones coming from Earth. But we've been talking with them and working with them on getting systems certified for their use. And so working with them on potential issues in space will be important. And then working with the CDRH and how that flows into laser safety offices at NASA and others to actually allow the use of these high power lasers is work that we've already started and will be continuing on. And I'll just end here, just showing some quotes, just sort of highlighting the pull from the US government, both NASA and the DoD, that we have been working to address and are continuing to advance. So let me again thank everyone, and I will stop there for any questions.
Great. Why don't we do introductions and let the questions populate the Q&A, and then after we get those, we can start having a discussion among the panelists as on the questions as they've come in. That way we can make sure that we've covered that spread. So okay, next up then we have Chris Davlantes from Reach Labs. So Chris, if you can come on your video, you can give us your video there. Oh, you're coming on now, I see.
Hi.
Yep, I hear your audio. Did you have some slides to
The host has stopped my video.
Oh, okay. Andrea,
Let
me see if I can.
I'm not much to look at. Oh, okay.
No.
Now we've started the video again. Hello.
Perfect. Yeah, and then if you, I don't know if you had to share your screen.
Yep, I'll share the screen right now. Give me 1 second. All right, so I believe you guys should be able to see my screen. Is that correct?
Yep, and it's got the right screen, full screen.
Great. Let me just minimize myself and put this up. All right. Well, thank you all for having me. It's, I think, apropos that I'm coming after Tom, since he's working largely on the optical side and we at Reach are on the microwave side. So sort of different strokes for different folks and different use cases around that. I want to talk a little bit about our current research, just a quick introduction to who I am, since you guys probably haven't met me before, and then a bit into the adoption challenges that we see for microwave power beaming. I know that we're tight on time, so I'll click right through it. Here we are. So as a matter of introduction, as I mentioned, my name is Chris. I'm the founder of Reach, and I have a background in applied physics and electronics from MIT. And Reach is a Series A startup, so we're still pretty early on in the space, and we focus mostly on building collaborative energy networks. So I'll talk more about what I mean on the network side of things, but that's really what is kind of our bread and butter, is building systems that can work together to add higher order network effects. So multiple devices can collaborate to form a mesh. Specifically, we work within this commercial energy infrastructure, where we try to establish power beaming infrastructure with defense and industrial clients and unlock incremental functionality through these collaborative expansions. So a lot of our commercial deployments are actually in Asia in some factories. And then we also have some sort of longer range work that we're performing on behalf of DARPA and some of the other DoD partners. This just gives you just a sense of the sort of problems we deal with. On the left-hand side, you can see we've got this little radio emitter over there that is a directed sort of metamaterial array and running at around 24 gigahertz. And it's able to send these multiple beams to small devices for servicing electronic tools. And that's really the level of most of the commercial deployments. On the other hand, we also have much larger arrays that we use for robotic platform powering. And those are more in the pilot stage, where they haven't actually hit industry in these controlled settings yet. So talking about collaborative energy transfer, and what I mean by collaborative energy transfer is the goal is ultimately to take all of the devices in a power network and mesh them together. So rather than having one transmitter that sends a beam of energy to one receiver, or one transmitter that sends beams of energy to multiple receivers, we can actually open up the paradigm and allow each receiver to partially absorb and partially redirect incident energy. And we've had some good strides on this, and most of our research as a company lies into how can we apply collaborative mesh algorithms and metamaterial structures to be able to allow the full network to reconfigure itself for optimal energy guiding throughout some scenario, some setting. And this lets us have extra degrees of freedom that overcome conventional issues in the microwave regime, like RF range limitations and of course line of sight. So similar to what has been mentioned prior about establishing kind of a mirrored pathway where we can bounce lasers around, we use our metamaterial apertures on the receive side to partially receive and partially redirect energy. And so the goal of this, I know that we've talked a lot about space in this conference, but ultimately, when looking at establishing more and more power beaming links, I tend to believe that the first instantiations are going to happen in commercial settings terrestrially, commercial and defense. And the ultimate goal of widespread adoption is to have, some sort of utopian type scenario where your electric vehicles can send energy to your delivery drones, which can partially redirect it down to, agricultural sensors, and everything is controlled through this large scale network that balances energy supply and energy demand. And this is really based off the idea that there's not much of an issue of available energy in the world. It's more about how we distribute it and how we manage our energy resources. So our goal as a company is to try to build towards this utopian future in small incremental deployments that ideally can expand in a seamless way through mesh networkability. Now, obviously, we as an industry, I think, are pretty far away from that. And there's a lot of different items at play that need to be put forth before we can get there. I view there as being three main buckets that are inhibiting the practical adoption of power beaming infrastructure. And I find them to be technical, market, and policy. Of course, technically, I can speak most about the microwave side of things. But I think market and policy, everyone is going to have their own demons to deal with in that regard, regardless of the technology modality. So on the microwave side, technically, we deal with this trade-off between aperture size and transfer efficiency. So although a lot of the work in the optics community deals with this as well, but not to the same level because the wavelength is so small. For us, you could have a 100 gigahertz aperture, but then your power conversion becomes much less efficient at those frequencies. So you have much better beam collimation, but much less efficient power transfer, ultimately, versus the other end of the spectrum, right, is a complete opposite. So there's this trade-off between the aperture size and efficiency that needs to be considered based on the application. And ideally, there's some Goldilocks zone where there's one best size fits all. On top of that, we deal with precise and efficient wavefront control. So you can imagine if you are truly trying to make a network that passes energy between all the receivers and has this collaborative sharing effect, that requires more than just simply some phased array transmitter running to some rectenna receiver. There's actually much more involved electromagnetic structures that need to be researched and developed for that. And getting that inexpensive is a big hurdle for the community, although there's been some metamaterial research that has helped out in that regard. The other thing that I think that we probably think about more than some other members of the power beaming community is truly how the distributed devices collaborate, right? So if we have a full aggregated network of all of these different power beaming infrastructures, how do those talk to each other? And how do those determine the appropriate ways for energy to be transferred so that everyone gets the resources that they need with minimizing the amounts of sort of consumption and maximizing the efficiency through the network? Now, of course, none of this really matters unless you're able to get market fit. And one of the things that it's great to hear Tom talk about, and also we focus on very much, is figuring out the right niches in the market so that we can start deploying these things in the real world, right? So that we get out of being solely in the research community and more about really driving these forward. In order to drive forward in the market, systems need to be affordable enough to be able to create a strong return on investment. So there's no real purpose in building a power infrastructure in a factory, for example, if it costs 20 times more than building 3 more factories, right? There's some trade-off there. So you have to ensure that the devices are economical enough to be able to be adopted in their applications. One of the, I guess, benefits of working with the defense sector is that there's oftentimes, as Tom showed through that series of quotes, there are often times where the lack of a flexible energy infrastructure can be directly tied to loss of life. And in that case, the market question is just out of the picture. It doesn't even matter what the cost is. Also, that was alluded to earlier, is that there's this chicken and the egg problem, where the receivers should be tightly coupled with the transmitters in terms of their designs. And in order to have receivers that are truly ubiquitous, you want to have some sort of network. But in order to have the integration or to establish the network, you need to already have the receivers integrated. So there's this market trade-off with how you're able to deliver value through incremental opportunities. The final bit, which I think everyone can relate to, is on policy. And I placed in the talk about safety in the policy section rather than on the technical section, because as groups like PowerLight have showed, there are a lot of ways that we can make power beaming systems completely safe. However, there is a public perception in the commercial communities and outside of the research community that these sorts of solutions are not safe. And I think that we as a community need to invest more in education around how these are safe and how they're able to be adopted in a way that is not detrimental to society. And on top of that, and inclusive of that, we need to have more comprehensive regulatory frameworks established for how these systems get certified. Currently, I'm sure Tom and others feel similarly that the application scenarios through which we're allowed to establish energy beaming links are quite limited because of the lack of clear regulatory frameworks. And so I think part of our job as a community should be to drive forward all 3 of these buckets in tandem to be able to ultimately deploy and get to that sort of more utopian future. Happy to talk more on a technical level, but thank you guys for having me here for quick seconds.
Great, thank you very much, Chris. Yeah, so great to get perspective from a voice that we don't often or always have in our typical telecon. So yes, I see Dawn has already started screen sharing. So yes, Dawn, you can go next with your challenges for power beaming. Thank you very much.
All right, can you guys see and hear me okay?
Yep, I see you.
All right,
and you've
sounds
got
good.
your screen on in the right way.
All right, perfect. So I was going to take a different approach from the 2 other panelists here and not talk about specifically what NREL does, but sort of put into context everything we've discussed yesterday, a little bit of today, but unfortunately I didn't have time to rework everyone's slides that I saw today into this presentation, but I did for everybody that went yesterday. So it's burning the midnight oil trying to put this together. Hopefully it helps. I was struggling mostly due to my background. So I was a former Marine. I spent 11 years on active duty. Then I spent a little bit of time as a project manager for a telecom company that made cell phone tower emitters. And then I got a PhD in material science, and I've been at NREL since. So the 2 sides of me that were struggling there was, what does this concept of operations look like for power beaming, and where does the technical limitations sort of fit in? So I wanted to start just with a quick caveat too, that if you see any numbers in here that estimate efficiencies or something, they're ballpark. So I used very rough significant digits here, okay? Okay, so it's not clicking there, let's see. Here we go. All right, so overall in this scenario, what I'm viewing is we have some sort of power source. It's generating the power that we're trying to beam. and it's trying to get some load. And I made a little rover over there on wheels that is there for exploration or digging or something, right? And they have their own challenges. One is, what the generation tech can be for its weight, volumes, et cetera, how it can scale. And on the load side, we've had a lot of this discussion about load demand. Does it have to be continuous? Can it store it? Lunar night, et cetera. But what we want to focus on here is everything that's in between that's connecting these two. And that's what I'm going to call the power beaming realm. And if we start at the load end and we assume that we only need, let's say 100 watts to start with at an early phase of this service deployment, we need to try to work backwards through this power beaming scheme and figure out what we have to start with for a power source, because that's going to drive all of the mass and everything else that we need to send to the moon. So on top of that, though, like I said earlier, what's killing me is the distinguishing, or which one should be driving which here, is the ConOps and the technology. And if you want to make it a little bit more complicated, if you're not happy with where the technology is now, we heard a lot about that, about the millimeter wave technology yesterday. You can invest in some R&D, and in time you'll get maybe some higher efficiencies at those technologies, but we're not exactly there now. So this is sort of a complicated chicken and egg thing again, as to what is the system going to look like, and do we have to develop the ConOps first or the technology first? And I think that's where maybe this panel should lead this discussion. And lastly, two things I'm not going to discuss in the next slide, but of course we always have to consider mass and volume when we're going to the moon. Okay, so let's start building out this power beaming system. So I'm just going to start with my power source. And I know that we have a series of steps here that we've been talking about. First, we have to have some sort of fuel that's converted to DC, and then probably some internal DC-DC conversion, a DC to some sort of electromagnetic radiation. That's what EM is. We then have to shape that beam, has to go through the atmosphere, has to hit the receiver, and then has to be converted from electromagnetic radiation to DC again. Then we likely have another DC-DC conversion for whatever the rover, whatever it is that needs to do it, and then a DC to work, whatever that rover is trying to do, either explore or to actually dig. So I just wanted to list these over here because each one of these steps represents a loss. None of these are going to be completely 100% efficient. And I know earlier that I wrote down the name Brian Turner said, efficiency is not the figure of merit, but I just want to keep this in context. I agree with you, Brian, but bear with me for a little bit. All right, so the power beaming is basically going to be in this realm here between steps 3 and 7. I'm going to include a little bit of the DC-DC because that could be integrated into any of these systems. But if you're trying to, use gallium nitride for all your power electronics, I wouldn't call that a specific challenge for power beaming. I think that's a power electronics challenge for a different community that we would just use. So with those DC-DC efficiencies, I'm going to call them about 90%. That's probably a gross underestimation, but I'm not quite sure what lunar conditions do to DC-DC conversions or what may be happening inside, but I'm just going to place those there. So first we have our power conversion. So we take that power, we're going to form it into some sort of electromagnetic radiation. We're then going to have to shape it with some sort of diffraction or optics. And altogether, this thing is the emitter. And some of the challenges there are whether or not we're making coherent or incoherent light, what the optics and beam quality of that is, whether we need continuous or pulse, and that relates to the concept of operations I was talking about, what the emitted efficiency is and what that spectrum looks like, because both of those will speak to the heat dissipation or maybe as a resource to be used by that system inside. So for those efficiencies, I just wanted to see all these on the same slide. I know they were kind of scattered everywhere in the previous presentations. So DC to microwave, they're roughly 85 to 95% efficient. DC to millimeter is 50 to 60. I looked that paper up this morning. I was just trying to get a rough order of magnitude. But again, that's small scale. That's a low tier L thing, which we'll talk about in a bit. And then DC to laser are probably in the same ballpark of 50 to 60% efficient. Again, grant me some freedom as to whether I'm only using 5% is my cutoffs here for how big my percents can be. Okay, so we then also have the optics. So we're either using diffraction or optics, depending which one of those above, and I'm going to assume those are about 90% efficient. So then we're going to transmit. So we're shooting our light across. This is the transmit region where we're going through the atmosphere, which is mostly noble gases, but we also have to be mindful of dust and the distance that we're trying to go through. Any safety considerations would have to be put in this category for eye safe or burns, or if you're hitting something else on the moon that doesn't like this radiation. And I'm estimating that this is about 98% efficient. I think that's more of a terrestrial Earth estimation, but I don't know honestly how each of the microwave, millimeter, or laser treat noble or are attenuated by noble gases, and or what level of dust we'd have in the effect there. So those are probably things we need to study in the future. All right, next we have our receiver piece. So this is going to have, some sort of antenna or a PV array. And challenges here are going to be with the aperture size based on which one of these systems we use again, or which electromagnetic radiation we're using. The collection efficiency, so how well we can focus that beam onto the target. And then the conversion efficiency, which is materials related, as to how well we can convert that electromagnetic radiation back into DC. And then that's related to heat dissipation. I just wrote in there the dual purpose. I've heard it before that maybe we can point this thing at the sun if we don't have the power beam, or I'm sorry, the power beaming source on. So typically we're going to collect about 95% of our electromagnetic radiation. Again, distance, aperture size, which sort of electromagnetic radiation is all going to play a part there. And then a summary for all the different microwave to DC, millimeter to DC, laser to DC are put there. So microwave is the most efficient, millimeter is the lowest, but again, that's because it's very low TRL, and lasers are about 50 to 70%. And I think that 70% came from the paper that Dan Friedman had presented earlier today. Okay, so trying to work backwards here. And if I try to start with 100 watts and work back through all these different percentages, we're gonna have to start with about 170 to 216 watts for microwave, 700 to 840 for millimeter, and laser is gonna be 350 to 590 watts to get 100 watts at the far end. Again, ballpark estimates, but I'm just trying to show you guys the trends here. And that millimeter wave is because it's very undeveloped, but it would likely fall somewhere between the microwave and laser efficiencies. So those colors would get swapped red and yellow if we invested in some millimeter R&D. Okay, so what I was trying to do here was get all this in one slide. And if you try to take the power as the sole source of what your figure of metric is going to be, or figure of merit is going to be, you're probably doing it wrong. So I kind of made this little chart here to show what the efficiencies were, the coherence, their effects with atmosphere, aperture size, receiver efficiency, and then the general TRL. So I'm here at this point. I know this is an incomplete data set. This is the end of my slides though, but I'm hoping that this will serve as maybe a visualization for the emitter, transmitter, receiver, or the whole system to help our panel discussion as to where we see the biggest technical challenges. And I'm not going to talk about policy or political stuff either. I was just focused on the engineering and physics piece of it. That's all I've got. Any
Don.
questions?
Yeah, thank you very much. I think this is a great, succinct summary. You did essentially a lot of the work that I have to do. So definitely don't, maybe I should screenshot it, but I'd really appreciate it if you sent this along as
Andrea
well.
has it.
Oh,
I think I moved some stuff, or I think I added efficiency here because
yeah.
But anyway, Andrea's got the majority of the slide here from this morning.
Great. Yeah, I think it's a very practical overview, as Chris says in the chat. I agree with him. So
like I said, I apologize. Everybody that went today, I didn't get to include your content. So
yeah, so I would quibble if only with the red, yellow, and green, because maybe they're not all evenly distributed. You rank them that way, but
I went with simple stoplight coloring to give your eye something to easily understand.
And I think that's something we can discuss once we get all the panelists through. And I think we've just got a couple more, but this is a great practical overview. So have it at the ready, and we'll have Q&A can still populate all of our attendees, and other panelists can also populate the Q&A with their questions while we hear from the remaining. We've still got a couple panelists to hear from. So next we have Murad Okandan from Empower. Murad, if you're there, there you are. Go ahead and give us your overview and your reflection on what you think the challenges and critical steps could be.
Sure. Thanks again, Wes, and thanks to the LSIC team and all the panelists here. I really don't have any prepared slides, but again, just really benefiting from the colleagues that have gone earlier. Again, there are technical challenges, there are regulatory challenges, and lots of others, but I just wanted to mention Empower Technology in terms of who we are and what we're doing. So I'm Murado Kandan, CTO and founder for Empower Technology. And we are deploying highly resilient, cost-efficient and low-mass solar power systems that are leveraging the high-efficiency terrestrial PV manufacturing technologies and microelectronics packaging technologies at the megawatt, tens of megawatts, and beyond scale for space power. So I think this is going to be quite interesting in terms of how much power is initially available in terms of what systems you could then consider building later on. So there's a big advantage there, we believe. And also for the beamed power systems in terms of having systems that can be easily deployed, retracted, and redeployed if need be for power beaming systems. Again, our technology has great applicability there. So again, we can get into more of the technical details in further discussions, but I also wanted to highlight one very critical metric here, and that's the levelized cost of energy. Dollars per kilowatt electric delivered, or primary generation of it, or if it's power beaming case, that applies to that larger overall system in terms of primary power into final power delivered to whatever the end user is wanting to do. And based on, again, some of the conversations here, I would include the cost per kilowatt hour thermal or unit of energy, thermal energy that's delivered for final use as well in that equation. So if we're thinking about deploying tens of kilowatts, hundreds of kilowatts or megawatts and beyond for lunar or other space deployments, the cost is going to be one of the primary determinants in terms of what can be built and delivered and rapidly as well. So with that, I'll probably go ahead and stop for now and then hope to participate in discussions.
Yeah, great. Thank you very much, Murad. And we'll get the discussion going in just a moment. We've just one more panelist to hear from, and that's Bill Nesmith. If you want to come off mute, if you can. I know that you have some intermittent connection, but you're with us, so you can give us maybe, we've heard from you already yesterday, but maybe give us a brief reminder and tell us your thoughts on what you think are the imminent critical challenges and what we need to do to advance power beaming.
Sure. The thing that I'd like to add is that to kind of understand where JPL would be coming from in this area is that certainly since our charter is the robotic exploration of the solar system, we would be very focused on missions and technologies that were further enhanced or enabled with this particular technology. And just as kind of an example, we start out, we do things like some of our most basic power systems we tend to be the radioisotope thermoelectric generators that will carry on board for deep space missions. And we do actually, some of the design and development for that technology. But oftentimes things happen that we, for example, have spacecraft like Voyager 1 and 2 that are running off those same RTGs now for 43 years, still sending data back. So certainly we approach our technologies through a view of what are the failure mechanisms, what can we do to enhance them and understand them so that we can predict them, even how they would perform, say 43 years in the future, when we certainly don't have 43 years to test our technology in terms of lifetime before we launch. One of the other things that we have to deal with is that a lot of our missions, they cover a spectrum from the discovery all the way to the flagship missions. But if we are talking about flagship missions, these are things that are usually in the billions category, particularly for deep space. The thing that is always a challenge for a project manager is the implementation of a new technology, because the last thing you want to do is to lose a mission, lose the data that you were hoping to acquire because of a risky technology. But I believe at JPL, they have come up with an approach to try to deal with this that I think the power beaming people can learn from. For example, the very first rover that JPL landed on Mars was the Mars Pathfinder rover, and it was just considered a small technology demonstration rover. Now, as a result of that, we went from something that was the size of a microwave oven to the Mars exploration rovers, which were about the size of golf carts, and we had 2 of those, and they operated for many years, beyond their design life. And part of that was understanding and developing and taking risk on certain things, like in that case, lithium-ion batteries, and demonstrating the lifetime, the cycling, and the environment. And then the next generation of rovers were about the size of the SUVs that we normally see, and about those kinds of weights. And it would had an RTG on it, as opposed to the other 2 just had radioisotope heater units on them, but they have been very successful. And even in the most recent rover, Perseverance, that we had, we also carried with it a technology demonstration of a helicopter. Again, a small one, but it was the first time powered aviation, I guess, was demonstrated on another planet. So the thing that's rather unique is that since we are always trying to go to unique places and we have to address unique environments, we need to be thinking in terms of, okay, as we go, we work with solar arrays, solar cells, but we tend to go to environments where we have lilt issues that we have to deal with. So we're used to dealing with the components that are rather unique to it, as well as trying to deal with things like the, let's say, shift in the spectrum that we find on Mars. But showing a path forward and how we can do small demonstrations and then have that turn into a whole series of missions, I think is a very smart approach for us to have. So
great, and I mean that's a perfect way to lead into some Q&A. Did you have another thing to say there? I'm sorry, I didn't mean to cut you off.
I think that's good. That's it.
Great, thank you very much. So you hit on several things that I think that were brought up sort of in short periods over the past few days, and I'm curious to hear from our panelists on some of these as well. One of the things that always sticks out for me is the failure mechanisms and mode of failure, how it's not especially considered always in the trade that we're considering. And when we're looking at our figures of merit and comparing efficiencies. So I'm curious what you think about, what the panel thinks about, modes of failure for power beaming, and especially as it may compare to cabled power transfer.
Yeah, I think in the some of the breakout room discussions yesterday, there was a lot of discussion of dust, and I think the failure modes, for example, of diode lasers, is their output sort of slowly decreases over time, and on a statistical basis, you might occasionally see some fail, but usually it's just their output slowly goes down, and eventually it's not worth operating anymore. And so, and then when the dust comes into the figure, you'll have more other efficiency losses. So from that perspective, it'll be a matter of really planning for end of life performance and what you need, however many years down the road it is, 5, 10 or more years. Is going to be one of the things to look at that's not necessarily a direct failure, but a like someone said yesterday, there's the nameplate rating versus the real world performance.
Yes. And so with I mean, there's a question too of modularity. If these, if the diode lasers, as they decrease in their, efficiency or start to fail, can they be made to be swapped out?
Right, and I believe that's the way a lot of the manufacturers make them and plan, like IPG and the others. They sort of overbuild them and spec them so that there are so many more additional diodes, so that at the end of their lifetime, they'll still hit whatever performance they quoted. I presume you don't want to do field service work on swapping out diodes on the moon. So it's a matter of just adding in extra capacity.
Well, I mean, we may at some point want to swap them out, depending on how long we wind up staying. Let's see. Did Murad?
Yeah.
It looked like you had something to say. Go ahead.
Todd or Tom, you had included in your charts a caveat with respect to plug-in and plug-out technology. Arguably, in terms of what we're dealing with power beaming and a lot of the electronics, it would seem that there's a potential for convergence, and regardless of the frequencies that you're dealing with in terms of the supporting electronics, and the ability to establish degrees of redundancy and reasonable failure tolerance with respect to the equipment as the underlying infrastructure. We're not quite where the only thing that's different is aperture, but the goal of being able to have a foundation of both plug-in and plug-out hardware technology and support a software driven level of evolution with respect to optimization would seem to me to be a practical and pragmatic approach. Is that in line with where you're thinking, or do you think the caveat that you offered has a broader applicability?
Yeah, no, I think you're right on that sort of component level for electronics. My point was more at we've had some people pushing about, as a subsystem, the entire receiver being made by one group and the transmitter being made by another. And eventually you'll be able to have them swap together. But there's a lot of nuances of optimization for design and communication between the two ends that is still very early. So that was only my.
So hold on just 1 second. I want to make sure that we give the panelists their chance to answer this as well. And one thing that I do want to bring up to this too is that we have a modularity and standards as a developing subgroup in our area, so we're pursuing that as well. So go ahead. I think Murad had something to say as well.
So just a quick comment. Again, modularity and being able to swap in, swap out is incredibly important. Is going to be a must in all the systems. One thing I wanted to mention in terms of our technology, it's actually built with that from the device level up. We have lots of individual cells, or let's say units, that are meshed in a very dense series parallel combination, and that gives a lot of resilience, both in terms of solar operation or beamed power, in terms of non-uniform illumination or dust, let's say, accumulating or being pushed off. Again, if it doesn't come off in a uniform way, you need to be able to accommodate those. So I think it's going to be critical that however the systems are built, they have inherent graceful degradation characteristics, so it's not a single point failure that takes everything out. And then modularity, that you're able to swap things in and out in reasonable block sizes, that gives you redundancy at the system level as well.
And it sounds like Tom, what you were mentioning was kind of the difficulties with having modularity around a specific beaming system, right? Because there's very tuned apertures in that case. But Gary, it sounds like you're mentioning more of a modularity on the powertrain side of things, right? Where you could actually have a singular box that doesn't matter if it's interfacing with microwave or millimeter wave or optical, that runs the maximum power point tracking and runs the conversion. And that seems like a pretty standard and easy place to start for building that type of modularity into these systems.
That's
indeed. Now, a quick follow-up on this in terms of a data point. When we were doing the robotic systems, interface standards for space station, we ended up, there was a selection of folks that went through. We did a competition and pulled together a whole bunch of different candidates, and all of the candidates finalists were convinced they had it all figured out. Okay, and what we did is we had them provide test articles, and we did a round robin, and every damn one of them, when that round robin process turned out to behave differently than the folks that offered them up had thought. Okay, so the sooner that we can actually get into a mode where we're, in a sense, testing the end-to-end system in terms of the ability to deliver real, real utilities. And I quite frankly think it's not just power, but it's the ancillary services as well that'll be integral to this service. That gives us a foundation so that we know what we're able to do, and we can see at least the next few steps forward as to how we can make progress with it. Over.
So there's actually a really interesting parallel here to telecommunications industry historically. If you look at Bell Labs and the setup of the communications infrastructure, you had to actually have the same company making the handset, the receiver, the lines, the repeaters, amplifiers, and the line at the end, so they could actually ensure proper functionality. This is early 1900s and on. Now that implied a monopoly, and that monopoly was a natural monopoly that was somewhat well managed, still to be determined. Similar thing on the utility scale, terrestrial PV, actually power industry right now. That all said, I think this is to Tom's point, there has to be some initial consistency throughout the system so you can actually have it function. But at some point, you also need to be able to diversify and be able to swap things in and out and further optimize. But I think that's going to happen organically one way or another.
Yeah, and I completely agree. My point was that forcing it too early can make it harder and slow down the actual ability of the technology to be fielded.
Now, on both of those points, and I love the analogy with telecommunications, especially with the two-part system, right? Like introducing the telephone as a two-part system, same sort of way that power beaming is a two-part system. I would view sort of as we start to develop more real-world power beaming applications, they'll likely be point-to-point at first, but ultimately, I think that one of the dreams is to have this flexible infrastructure, right? A flexible grid infrastructure where you can truly have interoperability. So on that level, as you all were mentioning, lasers got some advantages, microwaves got some advantages. It'd be great if we could swap those in and out. How do you all view the sort of the back end, the software layer of this that allows sort of like a laser system to communicate with a microwave system, to communicate with a magnetic resonance system, which isn't even power beaming, but related in the same sort of vein? Do you guys view that there will be a cross-industry standardization of the communication protocols as well? And how do you think that would play out between like the types of companies that we have here?
So I'll just make two comments. One comment, this was briefly addressed, I believe, Wes, in one of the standardization discussions actually with DoD lead on some of those systems. So that probably is going to be a key thing. And then the second comment, actually, there's some really interesting concepts and thoughts around this in terms of this interoperable energy infrastructure, whatever the providers are, whatever the consumers are, and there are ideally optimizing let's say, artificial intelligence or whatever you call them, agents that are able to manage both the generation, distribution, and consumption of energy with the requisite bookkeeping, optimization, and everything else. So there are concepts out there, but that's exactly right. We need to be able to think about what that end state is and make sure whatever we're building is, let's say, compatible and extendable further, so we don't get locked into a single infrastructure.
And my point around having that discussion going, and maybe it's something that Wes is already driving, is that, for example, with our networks at Reach, we have a very clear way that we'll integrate with like a factory system, programmer, logic controller, et cetera, and the way that we will deal with our networks passing energy between each other. That said, I'm sure PowerLight has their own separate protocol, and if we had a full network of a combination of different companies, right now, there's no way for us to talk to one another. And ultimately, as you're mentioning, Murat, that's got to be something that is an obstacle to having the true widespread adoption of this flexible energy infrastructure that people are searching for.
Yeah. If I can get back to Wes's question about failure modes, I'm assuming that on the moon, especially before we have dozens of people there ready to do service swapping of hardware, I'm assuming it's mechanical components that move that would be the most likely failure. And I'm just haven't really dived into thermal management systems on the moon and all the high power lasers. And I'm talking multi-kilowatt lasers that have multi-kilowatt or tens of kilowatt kind of cooling requirements, are condensers with water loops, with pumps and everything, which I assume we don't want to do on the moon. I'm just wondering what people have seen, and is there anything out there on that aspect that can be, do the thermal management in a way that's not going to fail?
Thermal drives design all the time. This is for spacecraft especially, right? We know that this is true. And one of the points that I always come back to is, if it doesn't fly, it doesn't scale. So if we don't start doing power beaming for this, ideal, what seems like the ideal, I think we called the killer application yesterday in a lot of the discussions. If we don't do it for that, we won't ever even have to consider the question of what are the thermal management that needs to happen when we get to that kilowatt beamed scale. I think that we have, very interesting potential role to play, especially in the exploration aspect of a lot of what we're doing. And we saw very, innovative ways to get to that, which I think are also very pragmatic. And that confluence seems to be very rare, right? When you have innovation and pragmatism kind of overlapping, it seems like it's a really good idea. So I'm interested in seeing how we can find that and sort of move that forward explicitly. So Chris, you had something to say too. I'm not a panelist, but I think that's an important thing to keep in mind.
Oh, no, I don't think so. I guess, Tom, a question for you is the main problem with the high power lasers. I'm obviously not a laser guy, but is it with the single heat generation source as opposed to some distributed heat generation? So like, for example, if you were to have a bunch of low power lasers and run through a combination aperture, would that alleviate the thermal issues that you guys have?
So diodes, whether you have a diode laser or a fiber laser, people mentioned IPG, the fiber laser is pumped by diode lasers. So all lasers that you're going to use have diodes in them. And they are often individual low power diodes, maybe single digit watts, or in some cases, 50 or 100 watts. And then you have a broad array of those. And so they are physically distributed, but ideally each of those is a very small concentrated heat source. And so it's not that you have to get rid of a few hundred watts per square centimeter over a full square meter, but you have a bunch of these intense heat sources that are spread out. And so it's a question of, do you just spread them out and have an extremely gossamer kind of structure, and now you have extra mass to hold it all to control that mass, or what? And also the diodes, generally they try to keep them below about 35 centigrade or so. They get more efficient at low temperatures, so that's great, except for the CTE mismatch problems. But if you're in thermal noon, the lunar noon in the thermal problem may make it hard to keep those at that 35 C. Your thermal resistance just goes way up.
Yeah, so I guess in that way, the heat distribution problem, and this is maybe another way of running standardization, sounds like it's not that far away from the type of heat distribution problems that folks deal with on the microwave and the millimeter wave side in terms of distributed amplification. It seems like the difference is 35 C is pretty cold, right? All things considered. So that's definitely got to be difficult, but that's really interesting. Thank you.
I hate to cut the panel off, but we have a lot of people in our attendees who can also participate in this discussion. They can do that a little bit better if we move to our breakouts. And we have breakouts which are explicitly for thermal. And hopefully the question that you were going to ask, Brian, I'm sorry I didn't get to you. I saw you raising your hand. But we can all transition now to the Zoom link, which I believe Andrea has just resent. So you can check your email to get back to get to that Zoom link. I'm sorry, I can't post it in the chat here. But if you all meet us over in that Zoom room, then we'll be able to do our breakouts and do all the beaming up and down of ourselves into those breakout rooms. And I'll go over what's going to happen there again when we get to that Zoom room. So I'll see everyone over there.